So we're going to continue on in this chapter, chapter 8, and it's all about bonding. So that encompasses ionic compounds, covalent compounds. Most of chapters 8 and 9 are going to be dealing with covalent compounds, but there is a little bit to be discussed with ionic compounds. And so let's go through that today. Okay, so ionic, we're talking ions. And ladies and gentlemen, you just need to know for general knowledge that ionic compounds, most of them are solids at room temperature, and they have a crystalline structure. Okay, something that might look like this. Okay, like a regular repeating pattern. Okay, ionic solids, obviously ions, positive charges, negative charges, opposites attract. So it's a very strong connection, guys. Ionic bonds are very, very strong compared to covalent bonds. Okay? So you get this regular repeating structure, and there's actually a word for that. Ionic compounds, the word we use to describe their structure is a lattice structure. Not lettuce, but lattice. Okay? A regular repeating pattern. And there's a term here, lattice energy. Okay? This is a term you use when you're discussing ionic compounds. And before we talk about lattice energy, let's review for a second. At the beginning of this chapter, there was a term, bond energy. Okay, and let's review how that's defined. Okay, bond energy, ladies and gentlemen, listen to the words carefully. Bond energy is the energy required to break a bond. Now think about that for a second. Energy required. Does that sound to you like an endo or an exothermic process? Endo, okay? Are endothermic energies positive or negative? Positive. All bond energies are positive, endo. So if energy is required to break a bond, what do you think happens when a bond is formed? Energy is released, and that would be exothermic. Guys, that's what lattice energy is a measure of. Okay? It's depending on how negative a lattice energy is. Because if all bond energies are endothermic, the opposite process, all your lattice energies should be negative, exothermic. And guys, how negative they are gives us an indication of how strong that ionic bond is, how tightly held together this ionic crystal is. The more negative it is, the tighter the connection. Okay? So, there is an equation here, which you can either write down or not, your choice. Right? It's not on your equation sheet. We're not going to be doing calculations with it. It is actually an equation we've seen before. It's something called Coulomb's law. It's a sort of more of a physics kind of equation. But it's a way to calculate something's lattice energy. Okay? K is just a constant. Don't worry about that so much. R is the distance between your two ions. Remember, we're talking about an ionic compound. So we have a cation, we have an anion. This is the distance between the ions. Let's talk about Q1 and Q2, and I'm going to give you an example here. Let's say you are asked to compare those two ionic compounds. And your job is to identify which one is going to have the more negative, the more exothermic lattice energy. Okay? Q1 and Q2, guys, those are the charges of the ions. Would you tell me, please, what is the charge of sodium when it's within a compound? Okay, +1. How about chlorine? -1. How about aluminum when it's in a compound? +3, and chlorine is again -1. Okay. Take these numbers. Here's Q1, here's Q2. We're going to put them right there. K is a positive number. +1, -1, whatever this is also positive. What kind of an answer am I going to get here? Something negative. And I should. We said all lattice energies are exothermic. Okay. What if I plug in these values here and here? Am I still going to get a negative answer? Yep. Will it be more negative than this one? Yes, it will. Okay. Aluminum chloride is going to give me a more negative lattice energy, which means a crystal of aluminum chloride is more tightly held together than a crystal of sodium chloride. Okay? Now, we are still in a time of year where when we take tests on material like this, you will see in free response statements. Just like on our last test, here's a statement. Your job is to answer in 2 sentences or less why that statement is true. Some people did very well on that section on our most recent test, some people not so well. You might have to explain something like this, and this is what the statement might say. Aluminum chloride has a higher melting point than sodium chloride. Okay, well, I haven't even said anything about melting point, but guys, what are you doing when you melt anything? What are you really doing? You're breaking bonds. Well, didn't we just say that a crystal of aluminum chloride is held more tightly together than sodium chloride? It should take a higher temperature to melt this guy. Now, how do you say that? Okay, because we're still in this time of year where you're going to have to be able to explain yourself in 2 sentences or less. So what do you say? What's the language? Here it is. If the statement said something like this, aluminum chloride has a higher melting point than sodium chloride, you would say something about the fact that aluminum chloride contains more highly charged ions. Guys, this is how you get around saying something like, well, NaCl was +1 and -1, and aluminum chloride was +3 and -1. You don't have to get into any of that. You would just say aluminum chloride contains more highly charged ions and thus will give us a more negative or more exothermic lattice energy. That's what you should say. Okay, so this is what I want you to do. I've given you pairs of ionic compounds. For each pair, I want you to tell me which one will give us the more negative lattice energy, or maybe the question would say which one has the higher melting point. Try these. Yep, number 3 is tricky. Let's talk it out. Let's talk these out. All right, let's look at number 1. All right, so let's say you come across a question, you're given these 2 ionic compounds, and you're supposed to come up with which one has the more negative or the more exothermic lattice energy. So you think, okay, I need to assign charges to these things. Okay, what is the charge of magnesium and oxygen here? +2 and, all right, and how about the other compound, sodium fluoride? +1 and -1. Which one of those is going to give us the more negative lattice energy? MgO. Okay. All right. Second one. Tell me the charges. Calcium fluoride, what do we got? +2, -1. Don't worry about the subscripts. They're not going to affect the charge. And aluminum chloride, we did this one. So what's the answer in number 2? Okay. Now, why did I say be careful with number 3? Number 3 is tricky. They have the same charges. +2 and -1. +1, -2. And so you might be thinking, well, then they must have the same lattice energy. No, they don't. Do you remember what this was in that equation last slide? What did this represent? The distance between the ions. Okay. Well, I'm going to ask you to compare the metals. Now, guys, I realize these metals are not in the same family. I get that. But strontium versus sodium. Which one has a larger ionic radius? Strontium. Let's see let's review from before our last test. Why is that? It contains what? More filled energy levels. Very good. Okay. How about, and again, I realize they're not in the same family, but iodine versus oxygen. Which one is larger? Iodine, definitely. Same reason. It contains more filled energy levels. These are 2 large ions. These are 2 smaller ones. Now just use a little common sense here. Lattice energy is an indication of how tight this connection is. Think about it. Do you think you can get a tighter connection with 2 things that are close to each other or 2 things that are far apart from each other? Close. This is going to give us the more negative lattice energy. If you would prefer a more mathematical explanation, we want this number for lattice energy to be as negative as possible. I need as small a number in the denominator here as possible. Okay, so the one with the smaller distance between its ions is going to give me a more negative lattice energy. Yes?
So would you write like, it has more negative lattice energy because it has more highly charged ions?
Okay, well let's talk about the wording here, okay? For numbers 1 and 2, your explanation would just say the compounds that we've circled contain more highly charged ions. That's all you'd have to say. For number 3, this would be one of these questions I would start with although these compounds contain the same charged ions, sodium oxide has a shorter distance between its ions, which will give us a more negative lattice energy. Do you want me to say that again? I'll say it again. So numbers 1 and 2, all I had to say was contain more highly charged ions. That's it. Number 3, although they contain the same charged ions, sodium oxide has a shorter distance between its ions, which will give us a more negative or a more exothermic lattice energy.
Would
Yes.
they ever like ask you like if there was like SRO and then like NAI? Like in
No.
like
No. Yeah, that would be, no. Okay. And really, this is about it for ionic, okay? The bulk of chapters 8 and 9 are on covalent, so we're going to move into that. We're just going to start into covalent, and that's all we'll do today. Okay, so let's just review from Chem 1, guys. In fact, everything we do today for the rest of this will be review. Ionic bonds. One atom loses electrons, one gains. There's a transfer. What makes covalent different? They share electrons. Okay? And there's a lot of forces at play here. The electrons of one of the atoms will be attracted to the nucleus of the other. Why? Why would those two things be attracted to one another? What in the nucleus specifically are the electrons attracted to? Thank you. The protons. Protons are positive, electrons are negative, opposites attract. There's also forces of repulsion, ladies and gentlemen. Like charges repel each other. Okay? These two atoms will form a bond length, a distance between them, when the forces of attraction and repulsion balance out. Okay? That's how bond length is determined. So what we're going to focus on today, and we're not going to talk about it for very long, is the concept of polarity. Okay? You learned this in Chem 1, so this should be review. Okay? We've got essentially three situations. Nonpolar covalent, polar covalent, and ionic. Okay, and I'm a visual person, so I'm gonna draw sort of in my mind how I think of these three concepts. I'll start up here. Let's say I have one atom that is A and another atom that is X. And these are the electrons for A. And these are the electrons for X. Would you agree that these two atoms are sharing that pair of electrons? Would you agree? Yeah? And I tried to draw it as best I could. Do you agree that that shared pair of electrons is equal distance between those two particles, those two atoms? That would be an example of a non-polar covalent bond. That pair of electrons is being shared evenly, equally. But what if they're not shared evenly or equally? Let's think about what that might look like. Okay. That pair of electrons is still between these two particles, so technically they're still sharing, but this atom is like hogging that pair of electrons, okay? That pair of electrons is more attracted to this atom than that one. They're not being shared evenly or equally. This would be a polar covalent bond, and it says if you have that situation, one end is slightly positive, the other is slightly negative. Whichever atom is attracting those electrons more, that's going to be the end of the bond that'll be a little bit more negative. This side will be a little bit more positive. Let's go to the extreme. okay? If it's ionic, and there's my little illustration here kind of has some limits. Okay, now my illustration here kind of breaks down because X doesn't even have a full octet of electrons, but the point I am trying to make here is these two particles, this pair of electrons is so attached to this atom and not that one that we can't even say that they're being shared anymore. This is really more like a transfer, and that's ionic. It's like it's so polar that it's not even covalent anymore. It's ionic now. And guys, it's a progression, okay? From nonpolar to polar to ionic, it's a progression. Right? And there's some vocabulary here, okay? Which you may or may not have seen in Chem 1. I don't know if our Chem 1 teachers use this term. You can say that a bond is polar, or if you want to be fancy, you can say that the bond has a dipole moment. Right? They mean the same thing. I also want you to be aware of this kind of notation if you ever see it, an arrow with a little plus sign on the other end. The arrow is pointing toward the element that is attracting the electrons more. Okay, so this side of the bond would be a little bit more negative, this side would be a little more positive. That's why they put a little positive at the end of that arrow. Okay. I just wanted you to be aware of what that arrow means. Okay. Now, how are you supposed to know which element is attracting those electrons more? You are supposed to know because you are a good little chem student and you remember this word, electronegativity. Okay? Electronegativity. You learned it in Chem 1. Let's review. It's defined as the ability of an atom within a molecule to attract shared electrons to itself. And before we took our last test, which was, a lot of it was on periodic table trends, a number of you came up and asked, is electronegativity going to be on this test? And I said, no, it's not. Electronegativity is one of our periodic trends, but because it's a concept that applies to bonding, we've got it in this chapter, not the last one. But one thing I want to point out to you, ladies and gentlemen, is the difference between electronegativity and electron affinity, because they have very similar definitions. I'm going to underline in this definition what makes it different than electron affinity. That's different, that's different, and that is different. Guys, electron affinity is the ability of an atom to attract an electron, meaning a single electron, to itself. When we talk about electron affinity, guys, we are not talking about an atom that is tied up in a chemical bond. We are talking about an atom just hanging out by itself. Electronegativity is a concept that applies to an atom that is bonded to another element. And it's how much does it attract not just a single electron, but that shared pair of electrons to itself. Do you all remember from Chem 1 what corner of the periodic table contains your most electronegative elements? Top right. Very good. Okay. What was that term we used a lot the last two chapters? It's a term that means how much a nucleus pulls on the electrons. What's that called? Effective nuclear charge. What corner of the periodic table are your elements with the strongest effective nuclear charge? Upper right. Do you think that's a coincidence? No. All periodic trends are a result of the strength of effective nuclear charge. The elements with the strongest effective nuclear charge are, for the most part, going to be your most electronegative elements. Okay? Now, I asked you to get a book. If you would, please, with your textbook in front of you, go to page 299. Okay, on that page, guys, there is a chart of all the elements on the periodic table, or most of them anyway. And you are given electronegativity values, okay? And we've got the trend there. You can look at the numbers for yourself. As we said, the upper right-hand corner has your most electronegative elements. So electronegativity increases from left to right. Let's see what you remember from our last test. Everything that is on the same row contains the same number of what? Energy levels. But as you move left to right, we get progressively more protons, which causes stronger effective nuclear charge. Good. Electronegativity decreases. You can see the numbers in the chart. As you move down a group, what happens as we move down a group? We get more and more filled energy levels. Very good. Okay. Do you notice in that chart, is there a family of elements that seems to just be sort of mysteriously missing? The noble gases. How come the noble gases are missing? I mean, they have effective nuclear charge. Why would they not be on an electronegativity chart? Because they contain what? 8 valence electrons. Okay, well guys, it's not even that so much that's the issue. It's an atom within a molecule. Guys, noble gases, it's not that they can't, but they very rarely will bond with other things. Electronegativity is atoms tied up in bonds. If you don't have bonds, then you can't talk about electronegativity. So we don't discuss noble gases. Now here's the deal, ladies and gentlemen. I care less about these numbers, which, by the way, I would not have you memorize. That would be stupid. I care less about the numbers in the chart. I care more about the difference in electronegativity between two elements. So, for example, you don't need a calculator. Please don't pick one up. What is the electronegativity difference, use the chart, between nitrogen and oxygen? What is the difference? 0.5, okay. What's the difference between carbon and oxygen? 1.0. Guess which of those two bonds is the more polar of the two? Carbon and oxygen. Guys, the bigger the electronegativity difference, the bigger the difference, the more polar the bond. Okay? What would be the electronegativity difference between an atom of carbon and another atom of carbon? 0. So what kind of bond would that be? A non-polar. Okay. How about the difference between boron and polonium down at the bottom? Boron and polonium. 0. Okay. So technically speaking, that would be a non-polar bond. Now, guys, would I expect you to know that boron and polonium have the same value? No, I wouldn't. Okay? But here's the point. If the electronegativity difference is 0, that's a nonpolar covalent bond. If the difference is intermediate, it's polar covalent. When that difference starts to get very, very large, we would now consider it ionic. Now, I can see the question in your eyes. I can see it like scrolling across your foreheads like the crawl on CNN. Okay? You're thinking, okay, well, what kind of number is intermediate? Like, what's considered a large difference versus an intermediate difference, right? Yeah. Okay. Because maybe you're wondering, well, how do I know where it stops being polar covalent and when does it become ionic? How do I know? Guys, go back to like the first month of Chem 1. How do you ever know that a compound is ionic? Metal, non-metal. So what's covalent? Non-metal, non-metal. Okay, so for example, look at the chart. What's the difference between aluminum and chlorine? 1.5. That's not a huge difference. I mean, that might fall kind of like in here, but if you're thinking like, I don't know, is that polar covalent? Is that ionic? Guys, aluminum is a metal, right? Nod your heads. Okay. It's definitely an ionic compound. Now, is it like a super duper ionic compound? Okay. We can talk about something called covalent character and ionic character. Aluminum chloride is for sure an ionic compound. Is it like a super duper ionic compound? Not as much as something like, I'm looking at the chart, cesium chloride. Cesium chloride has a much greater ionic character because it has a much bigger difference than aluminum chloride. Okay. So don't stress, like, how am I going to know? So this is the last thing we're doing. Use those numbers. This is very quick. It says put these bonds in order of increasing polarity. So the least polar to the most polar. Go. Okay, this is quick. So which one is the least polar in this list? HH. In fact, it's so least polar, we would call it non-polar. Okay, who's next in the list? After that, HCl, thank you. Then, and then PO is our most polar. Guys, is this one so polar that we would consider it an ionic bond? Why not? How'd you know that? It's still two non-metals, okay? It's just a very polar covalent. The last thing I want to say, because somebody asked this earlier, great question. Could I ask you this without that chart? Yes and no. Okay, could I ask you these exact ones? Maybe not. But here's what I could ask you. Look at your periodic table on the wall or the one in front of you, whatever, not the chart. What if I asked you which of these two bonds is more polar? OF, O and F are right next to each other, OF or NF? Do you notice on this chart here the physical distance that two elements are apart from each other on the periodic table corresponds to their electronegativity difference. The further apart they are, the bigger the difference will be. So you guys tell me, OF or NF, which one is more polar? NF. NF will have a larger electronegativity difference than OF. So I will stop here.